We analyze the data content of non-line-of-sight imaging measurements in the Fourier domain to better understand what type of scene features can be measured using non-line-of-sight imaging. We put our focus on the question which features we can actually resolve with a limited aperture size. In non-line-of-sight imaging, a hidden scene is reconstructed from measurements of indirect multiply reflected light. A light source illuminates points on a relay wall with short light pulses, and a fast detector records the light returning to the relay wall as a function of space and time. From this information, the unknown targets can be reconstructed. Multiple algorithms have been developed to perform this reconstruction. In this work, we take a closer look at the measurement operation itself. This allows us to make statements about the information captured that are independent of a particular reconstruction algorithm. Let's take a look at how we can describe the captured information. We define a so-called non-line-of-sight measurement function, an integral operator that describes the measurement process in the primal domain. We then perform a Fourier transform of this function, obtaining a so-called Fourier cone that describes what 3D spatial frequencies of the scene are contained in the measurement. Here we have a scene on the left and move the considered point along a line perpendicular to the wall. We find that the information available from the measurement actually has a conical shape, therefore the name Fourier cone. The size of the cone depends on the considered location within the scene. We can see how it changes with distance to the aperture. Similarly to the previous situation, we now move the considered point parallel to the aperture and see that the cone actually rotates around the center point. Let's now take a look at the Fourier space representations of different scene features. Most scenes can be approximated using a small set of local features. So knowing the Fourier domain representation of those features will allow us to gain an intuitive understanding of the information encoded in the scene that we would like our measurement to capture. A plane transforms to a line in the Fourier domain. A point transforms to a constant. Features such as edges, corners, and curvature also broaden the spectral pattern. Only the part of the spectral scene patterns that overlap with the local measurement cone can be reconstructed. This limitation is most evident when trying to reconstruct a large plane. The spectrum is a line. As the plane rotates, so does its spectrum. So what does this mean for our ability to measure surfaces? To validate our results, we perform reconstructions from experimental data. Consider this scene consisting of 3 identical patches. All are in the space in front of the relay wall and at similar angles. Patches A and C are parallel. However, the surface normal of patch C does not point at the used relay wall, but slightly next to it. Let's now take a look at the Fourier domain. The purple and the green lines are located at the same angle. The position-dependent cone that is actually measurable is shown in the next line. From the overlap of the cone and the scene features, we see that the spectrum of patch C is outside its local measurement cone. We therefore have acquired the information shown in the second row. So what does that mean for our reconstruction? Consequently, patch C is missing from the reconstruction and actually not visible. For more details, please refer to our paper.